Good morning, everyone. Good evening or good afternoon, whatever it is. Yes. So let's go with kinetic gas equation today. So kinetic gas equation, we know PV equals to 1 by 3 mn u square RMS or URMS square, whatever that you say. Okay. And then kinetic energy of n moles is 3 by 2 nRT, where n stands for the number of moles. And let us now see how did we get this. Although this will be taught to you in your physics, I am also giving you how to go with the derivation of this, how you would derive these things. So I will be talking about a molecule. Now, whatever molecule hits the wall of the container, that would be exerting some force on the walls of the container, which means force by the area. Okay, whatever is this much area we are talking about, force by that particular area is nothing but the pressure exerted by this particular molecule. And this molecule is moving with some velocity u, right? And if I say these molecules are in random motion, each molecule is in random motion, you have ux, uy, and uz component for that. So which we would generally take it as ux is equal to uy is equal to uz, which means if I say u, that is ux times I plus uy times j, because that is according to your ijk vectors plus uz times k vector. Now, if I have to take out the modulus of it, mod u is equal to under root ux square plus uy square plus uz square. And now, since we have already taken this for a given molecule, ux is almost equal to uy equals to uz. So that would be under root 3ux square. Everything is turning out to be ux here. I'm taking it as for convenience, ux, and ux, because ux is equal to uy is equal to uz. So this would be your mod u. So therefore, u square is equal to 3ux square. This is what we can take. Implies ux square is equal to 1 by 3rd of u, is 1/3 of u square. So let me put this aside. We will be making use of it later. Okay, so now we all know what is RMS speed. RMS speed is what? URMS. RMS speed. Speed matlab velocity. Okay, root means square speed. Square is, just read it backward. It will be easy to go with. Root mean square speed. Square is nothing but your square of the speed. And mean which means what? U1 square plus u2 square plus so on till un square upon number of terms there, number of molecules there. That would be, and you take a root of it also, because this is root mean square velocity. So which is also taken as 8RT by pi m. Okay, so this you will put aside, and let us talk about momentum. What do you mean by momentum? Because we are making use of all these. I'm just making everything available to us so that we will be substituting them in our further equations as well, further coming up things here. So I'm just getting everything ready for us to use these, equations here in our derivation. So now let me go with yeah. So what is momentum? P stands for momentum. Momentum is nothing but the state of motion of a particular element, whatever you're talking about, whichever substance we are talking about. The state of motion is defined by the momentum, and momentum is mathematically written as mass times velocity. So mass times velocity is uxi, I would take some random uxi. This is P initial. And let me say P final. Final momentum will be in the opposite direction, because the particle hits and then comes back. It hits with ui, it comes back with uxi with a minus. See, this is uxi forward. So it comes back with negative uxi, because these particles are in elastic motion. Elastic motion matlab, yeah. Elastic motion matlab your kinetic energy is conserved, which means your velocities are conserved. So therefore, it is coming with the same velocity in the opposite direction taken as this. P final is minus muxi. Now, what will be delta P? Change in momentum is P final minus P initial. P final minus P initial, which means this minus of minus this, that becomes these two equations. Minus of minus plus, this is 2muxi. So this is my delta P. I'm getting ready with my delta P as well. Okay, that is 2muxi. Now, time taken for each collision, time taken. So what do you mean by the time? Speed is equal to distance by time. So time will be distance by speed. Now, what is the distance we are talking about between the collisions? Okay, the particle goes, hits it, and then it comes back. So therefore, d and d, it is 2d by ux is my time taken for each collision. Okay, so this also I'm keeping ready. All these star marks I'm keeping ready so that we can use everything here in our final derivation. So now let us go on with our second law of motion, which you have done it in your ninth grade, yeah. So force is directly proportional to rate of change of momentum. So force is equal to rate is always with respect to time, delta t, which means delta t, and rate of change in momentum. Momentum is delta P, change in momentum, which we have already got here in this part. Delta P is equal to 2muxi. By delta T, here we got my delta T also, which is 2d by ux. So this cancels out to be here, which will be ux and ux. So m by d ux, the square, is my force. And that is the force what we got. And now we can use our force net here, net force. What is the net force? Due to n molecules. Net force due to n mol. What is uxi? That also let us write down first. 1 second. If you are done, just pause it up and keep going with the writing part. Everything once written, then move ahead. Otherwise, don't move. Okay, just keep pause it and then move ahead once you are done with all this. Yes. Now coming up with the next part of the framing up of the equation, what do you mean by force net? Net force is nothing but the force due to n molecules of it. So m by d times, and what is this taken as here? My what is ux square? I can substitute here in this part. M by d ux square is nothing but my 1 by 3 u square. That I am substituting here. So this is m by 3d u square. This is what we got. So now let me talk about the net force. Now net force, this is force due to one particle, and this is force due to n molecules. That would be m by 3d common, m by 3d common. I am taking it as now u1 square plus u2 square plus so on till un square, because f1 plus f2 plus f3 so on fn, right? So now what I'm doing is I know the formula for urms. That is what is here. urms is equal to under root u1 square plus u2 square plus un square by n. So which I see it in this format. So what I do here is by n into n. I'm just multiplying and dividing with n. Carefully you do it. Just multiply and divide with n there. 1 second, I'm just pushing my scale. Yeah. Yes, multiply and divide with n. What is this part? All this part is nothing but your u square RMS, right? So this is m by 3d. All this dabba here is my u square RMS times n. So n stands for the number of moles. Here I'm just putting it up. So now what is this? F by A, this is my force is equal to, this is what we got. Now, what do you mean by pressure? Pressure is force upon area. This is an equation we got. Now, pressure is force upon area. So now what is force? Force is the above thing what we got. So M N U square RMS by 3D is the force, and divided by area. Area is what? Area is nothing but distance square, right? Area is L into B, which is nothing but D into D. D square I have written. And D times D square is D cube. D cube is nothing but my volume, right? So Mn U square RMS by 3V is my pressure. So PV is equal to 1 by 3 Mn U square RMS. This is what we got. This is our kinetic gas equation. PV is equal to 1 by 3 Mn U square RMS. So this is the derivation which you generally will not be asked in your chemistry, but yes, physics ke liye it is very important. But yes, you should know how did we get this so as to use it in your numericals later. All right, so now pause it up and I want you to try this again using your own brains. All right, so try this derivation. This is very important derivation. Now, so what we have just now done, we have just calculated the force. I'll just recapitulate everything later. Now let me go with kinetic energy. Now what is kinetic energy? That is half mv square. That is what we have known. So this is now half mu1 square plus half mu2 square plus so on till half mun square. So m stands for the mass of that particle because mass of that same type of particles are the same. So I'm not taking it as m1, m2, m3 because mass remains the same for similar type of particles. Then velocity is also almost same, but since we are talking about these things, I am going with m, half m common, u1 square plus u2 square plus so on till un square. But now I know my RMS velocity, so by n into n I am doing. So now what is this? Half m, and all this is nothing but my u square RMS times n here. So this is half m, and u square RMS times n is nothing but 3 times PV, right? From here, from just now what we got. Okay, u square RMS times this is nothing but your PV, right? So which is what I'm going to write here. Oh, 1 second. Yeah. So from this equation, from the above equation, what we have just now proved, so this would be half times 3 PV, 3 PV, because all this to the other side, 3 PV is equal to Mn U square RMS. So that will be nothing but 3 by 2 PV, that is my kinetic energy, or which is 3 by 2 PV is equal to nRT, we know, so PV is equal to nRT. So therefore 3 by 2 PV or 3 by 2 nRT is my kinetic equation for this. Now let us talk something about what is this. If I take this here as my number of n stands for my number of moles. This is given moles. N is number of moles. Now 1 mole is equal to given mass by molar mass. And Avogadro number, if I have to talk about Avogadro number, 1 molecule, that is fine, but n molecules ke liye, that would be your by Avogadro number. So this is 3 by 2 times RT by Avogadro number of molecules. Now this R by N, which is nothing but your Avogadro number, R by N Avogadro, which is nothing but called as Boltzmann constant. Boltzmann constant, and Boltzmann constant is equal to 1.38 into 10 to the power minus 23 joules per Kelvin. So this number you should remember, ma. Okay, so R by Na, this is for n molecules, right? If I am talking about the total molecules there, so this is R T by Na. Okay, by Na. So this is for the, one particular molecule. If you talk about, then you divide it with your Avogadro's number. So which is 1.38. R by Na is your Boltzmann constant, which is 1.38 times 10 to the power minus 23. Write it as neat as possible. So I'm just going to recapitulate everything now. Yeah. So kinetic gas equation we have, which is nothing but PV is equal to 1 by 3 mn u square RMS. Where is this coming up from? I have a molecule. Okay, I'm talking about a molecule which is hitting my walls of the container. And as it hits the walls of the container with some force is exerted by this molecule on the walls of container. So force by area is my pressure, right? And if I'm talking about a substance which is moving, I need to also talk about its velocity. So V, velocity, is being taken as some initial velocity it is going on with. They move with random velocities in random directions. If I'm talking about a 3D plane where it is uxi plus uyj plus uzk. So, and then modulus, if in case if I say AI plus BJ plus CK, you have already done in your 3D geometry and vectors. AI plus BJ plus CK, if it is your R, vector R, then R का modulus क्या है? It is under root A square plus B square plus C square. And that is how you get this as under root UX square plus UY square plus UZ square. And since UX is equal to UY is equal to UZ, because almost the same velocities it possesses. So therefore, it is 3 times US square is your U square is equal to 3 times UX square. This is your equation 1 I talk about. And then we come with your momentum, because we are talking about force, pressure, and also come back. So pressure anangane, pressure is force by area. Force anangane what? Force is momentum, rate of change of momentum. So we have to talk about the momentum here. So momentum is initial mass into velocity. It is just nothing but your state of motion, mass times velocity, m into ux square. So P final is minus m into ux square, because it is moving with the same velocities because of elastic motion. Elastic motion is having conservation of momentum. There is no change in the velocities there, only the directional change is observed. So therefore, muxi, and this is minus muxi, the change would be 2 times. Because P initial minus P final you do, or P final minus P initial you do. This is my second equation, which I got. Delta P is equal to 2m uxi. So now I'm coming up with force. Force is rate of change of momentum, delta P by delta T. Delta P value we got, delta T value also we got here. It is equation number 3 here. Delta, value. So equation 1, 2, 3, I'm just shading it up. Okay, 1, 2, and 3. Yes. So speed is distance by time. Distance is what? Distance is nothing but between two collisions. Distance becomes 2D there. Distance here, this is distance, and this is also distance. So 2 distance it is. So 2D by UX. So UX is equal to 2D by T. So that is how we can write. So convert them here, put them into here, plug in just the values there. So delta P by delta T is 2m UXi by 2D UXi cancels. M by T UXi square. Now UXi square, we have already got it in our first equation as 1 by 3 U square. So I'm just substituting that. Now this is for force of one molecule I'm talking about. Till now we were talking about only one molecule, bachon. Okay, now we are talking about all the molecules together. Force net. Net force is F1 plus F2 plus F3 plus so on till Fn. That will be m by 3d is remaining the constant. So I'm putting it as common. Then u square ka summation. Summation of u square is u1 square plus u2 square plus so on till un square. Since I have it in the format of u RMS there, I'm trying to put it in as by n into n. So by n kiya, so I got this, all this as my u square RMS. I have substituted it as u square RMS into this. So force I got, and pressure is what? Force by area. So area is d square, because area is a into a, because we are considering it to be a cube, the distance into the distance. So that would be your denominator. As you can see, d into d square, it is volume, d cube, na? Volume, it is mn u square RMS by 3v. So PV is equal to 1 by 3 mn u square RMS. That is what we got as kinetic gas equation here. So this is how we get your kinetic gas equation. And then accordingly, I can get my kinetic energies also. Kinetic energy is half mv square, half mu1 square plus u2 square plus so on. So half m common, bring it in the format of u1 square plus u2 square plus so on till un square by n into n you would do. And then this is what you get. And this will be your 1 by 2 times mu square RMS. We just now got PV is equal to 1 by 3. Say this is 3 times PV. So 3 by 2 PV. So and PV is equal to nRT. We have already known that, right? PV is equal to nRT. So that is how you got. And this is for n number of moles. And I'm talking about here as you one particular molecule divide by your Avogadro number of molecules here. So there brings you your answer. So this is the integral derivation, which is very, very, very important. All right. Based on these things, we are going to do some numericals as well. So let us hold on to this and move on to the next topic here. I'm just giving a brief of your volume correction and pressure corrections also. Volume correction and pressure correction, because we are not talking about ideal gases anymore here. Ideal gas has got, elastic collisions, yes, and ideal gas will practically occupy negligible volume as compared to the volume of the container, because molecules do not react. But we are talking about some real gases where there are some interactions happening there. So because of those interactions, your volume of the gas occupied is a little more only. So, right, so now the volume, effectively the space for the volume of that gas, the space for the gas is now reduced. So that would be V of the gas, which means nothing but free space. Free space available. Free space available for the gas is now volume of the container minus volume correction. And what is that volume correction? V minus V dash, that is V minus NB. V dash is nothing but your N times B. B is nothing but your effective volume of 1 mole of particles. B stands for effective volume of 1 mole of the particles. And NB ante for n moles of particles. B is effective volume of 1 mole of particles in it. So NB stands for the n mole, because we don't have 1 mole. No, we don't know how many moles are there. Some n moles we have. This is your volume correction, and you have pressure correction. And pressure correction, as I just now have shown you, a molecule will hit, and that is nothing but force by area, right? So P real, okay, is ideal pressure minus P dash, and which is nothing but P ideal minus a n square by v square. Why is this n square by v square? Because this is P dash is a times n by v times n by v, because this is nothing but your concentration of particle A into concentration of particle B, although it is of the same molecules we are talking about. One molecule to the other molecule, we are talking about concentration is moles by volume. So that will be your a n square by this. So now if I have to substitute here in my ideal gas equation, PV is equal to nRT. This is for the real world. All this for the real world, volume correction and pressure correction for the real world. And here is my ideal. PV is equal to nRT is ideal. So now pressure ideal is nothing but P real plus a n square by v square coming up from here, right? Times volume is V minus NB is equal to nRT. So this is my van der Waal gas equation, I would say. This is van der Waal gas equations for your n moles of the gas. And here we have something called as critical temperatures, critical pressures, and critical volumes, right? So pressure critical is nothing but A by 27 B square. Please note these formulae, very, very, very important. Okay, critical temperature is 8A by 27 BR. R stands for your ideal, gas constant, right? VC is equal to 3B, and Vc is your volume, critical volume is equal to 3B. And based on this, if you solve 1, 2, 3 equations, you will get B equals to RTC by 8PC. So this you can mark it. This can be used in your formulations also. All right. And then comes up with something called as compressibility factor. That is also equally important because see, all this PV is equal to nRT, all the ideal gas equations, gas laws on one side, and today's class on the other side. So today's class is based on this real gas equations as well. That is on the other side. So now let us go with our, please take a note of this clearly, very clearly in your point wise in your notebook. Right, so next, going up with compressibility. So how is your gas compressed? How well is your gas compressed, I would say. So if I say PV is equal to nRT. Apply log on both the sides. I'm applying log on both. I'm just trying to derive something here. Please try to do it now. See, apply log on both the sides. Log PV is equal to log of nRT, right? So now log P plus log V is equal to log of nRT. Now this is log P and log V. This is log P and log V wala graph if I'm talking about. And it has some deviations to be observed. Now Z stands for compressibility factor. And what is Z? Z is equal to PV by nRT, which is nothing but your slope of the graph, right? So Z is equal to PV by nRT. Now, in case your PV by, or also V real by V ideal. The real gas, how much is your real gas occupying the volume of the gas of your real gas occupied by the volume of the ideal gas occupied. Now, if I say volume of the real is equal to volume of ideal, see, case 1, if volume real is equal to volume ideal, implies Z is equal to 1, implies PV is equal to nRT is your ideal gas case, ideal gas equations. In case your V real is equal to V ideal, it is your ideal gas equation. This is case 1. And case 2, in case your PV is greater than, or if I say real, V real is greater than V ideal, implies Z is greater than 1, implies PV is greater than nRT. In case PV is greater than nRT, your gas expands. है ना? Real, V real is greater, we are saying V real, matlab real gas has got greater volume matlab it is expanding. Gas expands implies it has got positive deviation as compared to the observed. And case number 3, what we have here, in case your V real is less than V ideal, which means Z is less than 1, which implies PV is less than nRT, then your gas is compressing. Gas compresses implies negative deviation. Why is it gas compressing? Which means it has attraction, more of attraction between the particles. And whereas here positive deviation, gas expands, implies repulsive forces. Repulsive forces are more as compared to your attractive forces in second case. Whereas here attractive forces are more. That's the reason molecules are coming together and it is occupying lesser volume. Now real gas is now occupying the lesser volume. So here comes up with your PV is equal to nRT, and these are the cases for compressibility. Now this is the compressibility factor Z. Depending on the values of Z, we will be able to confine case 1, case 2, case 3, case 1 for the real gas, case 2, if gas expands అంటే ఏంటి, repulsive forces are more. Case 3 is gas is compressing, which means attractive forces are more. So based on these these equations, what we have derived today, along with your VRMS, V most probable speed, all those, we are going to do some questions of your exercise 1B today. 1B today from your JE book we are going to do, and I want all the botany students to also follow this because this is as equally important to you to get good scores on your NEET exams, because the easy ones anybody can do. You are on your competitive edge, so you need to go an extra mile along with the MPC students so as to win those jackpot tricky questions. So here we start up coming up with our next set 1B from the JE. All right. So just take a pause and go through it once, go through all of this once and come back. Yes, so as we have just now thought of doing 1B exercise, yes. Which of the following is not true? The first question, which of the following is not true? Listen to me very carefully. All right, density of the solids is greater than gases. It is true. Yes, solids ka density greater than gases. Yes. Molecules of solids process vibratory motion. Yes, because molecules in the solids, they vibrate, they don't move from one particle to other, one position to the other, they just vibrate. So vibratory positions motion, yes, for the solids. And molecules of the gases possess greater kinetic energy than the molecules of solids, yes, because molecules of gases are moving, whereas molecules of solids are in vibratory position, in their mean position only. So all the 3 points are right. Number 4, gases like liquids possess definite volume. No, gases do not possess definite volume. They occupy the walls of the container. They occupy the volume of the container. Next, number 2, aqueous tension of water depends on. Aqueous tension always depends on temperature, because aqueous tension and TNT, like, if you have a, water or any liquid, that can be the surface, how much is that pressure it is being taken by the surface is what is called as your aqueous tension, right? And I'm having 4 options here: amount of water taken, volume of the container in which water is present, temperature, and some external other factors. No other factors, it is only the temperature. Imagine you have oil, okay? You have hot oil and you have very cold oil. Hot oil has got less aqueous tension as compared to your cold oil. Cold oil has got more aqueous tension, right? So as you can drop something over it, some jeera or something that floats, whereas for hot oil, it just may, come down in the oil. So therefore, the aqueous tension depends on the temperature. Next, number 3, you have Dalton's law of partial pressure will not hold good for which of the following? You have H2 plus O2 plus Cl2, Cl2 plus NH3 plus HCl, then N2 plus HBr plus Cl2, Cl2 plus NH3 plus O2. So Dalton's law of partial pressures holds good only in those cases wherein the reaction does not happen. Here, ammonium chloride gets released. Ammonium chloride gets released. So here reaction is happening. So therefore, it will not hold good for this second option. It is not holding good. The Dalton's law of partial pressures does not hold good for this, as it ends up in a reaction NH4Cl ban jayega. Okay, that's the reason. But rest of the things will not react. So therefore, no problem there. Next, at sea level, the air is denser at sea level. This can be explained by which law? Boyle's law, Charles' law, Avogadro's law, and Dalton's law. At sea level, the air is denser, which means you are comparing the air at sea level and air above sea level. Above sea level. So both the cases, your pressure is different, right? So pressure is different. So I don't talk about anything as constant pressure. Your volume of air is also different. So I don't talk something as constant volume. So here the temperature constant, keeping temperature constant, it is your Boyle's law. Boyle's law will define you. The air at the sea level is more, denser. That is what the Boyle's law is defining us. Yes. Here comes with number 5, question number 5. Slope of plot between PV and P at constant temperature. So as they say, at constant temperature, PV and PV on your y-axis, P on your x-axis. Slope of this graph is what? How do you gauge that? See, PV is equal to nRT. We know N is the number of moles constant, R is a constant. Now they say at constant temperature. So this also is your constant. So PV has to be maintained constant. No other way. PV has to be maintained constant only. Now at constant temperature, PV is a constant line. So constant PV is maintained at constant, which means your slope of the graph is 0 because slope is parallel to x-axis. Anything which is parallel to x-axis, slope is 0. Why? Because slope is given as tan theta. And theta is nothing but your angle between the graph and your angle between your curve and your positive x-axis. That is not meeting it at all because it is constant PV. So therefore, m is equal to tan theta and m is 0. So theta is 0. So therefore, any line which is parallel to it. So slope is 0 for this. Next, number 6, steam distillation is based on Dalton's law of partial pressures. What is steam distillation is based on? Is it based on Boyle's law, Charles' law, Avogadro's law, or Dalton's law? I would say it is Dalton's law, because steam distillation, it depends on how many number of moles of that particular substance it is there, so therefore Dalton's law of partial pressures, if you have A, B, C type of molecules in them, then each of the, pressure exerted by each of the molecules will be decided on how many moles they are in. So which will tell us the Dalton's law of partial pressures. Next, number 7, we have a helium gas diffuses 4 times faster than gas X, which means gamma of helium is 4 times gamma of some gas X. So I would write gamma of helium by gamma of X is 4. Find the molar mass. And if I say gamma 1 by gamma 2 is equal to under root m2 by m1, so molar mass of X by molar mass of helium. So which means 16 is equal to molar squaring on both sides, SOBS squaring on both sides. 16 is equal to molar mass by 4. 64 is molar mass of X. Here I have 64 as my answer. So sometimes directly molar mass given to you, sometimes molecules are given to you. Find out the molecules ka molar mass and then match it up with your 64. That becomes your answer there. So all right, I am moving on with my next question there. Question number 8. Please excuse me with my throat. I'm not good at my throat today. Yes. The average kinetic energy of which of the following gas is higher at same temperature? They are asking about average kinetic energy. And kinetic energy we have just now derived 3 by 2 nRT is my average kinetic energy. So therefore, now what is that? Say average kinetic energy of which of the following gas is highest under same temperature and pressure. You are given options: hydrogen, you have C2H4, you have SO2, and all same. These are the 4 options. So average kinetic energy always depends on, because N number of moles constant, R constant, depends only on the temperature. Remember that this type of questions are asked N number of times. Kinetic energy is directly proportional to temperature. They said it is same temperature, so all are same. So in this particular question, everything is same because kinetic energy depends only and only on the temperature, nothing else. So remember that and move on to the next question. Yes, coming up with my next question. An LPG cylinder can withstand a pressure difference of 15 atm. 15 atm is the pressure difference that it can handle across its boundaries. If at room temperature, which is 27 degrees Celsius, at 27 degrees Celsius, it is filled with 2 atmospheric pressures, determine the temperature at which it will explode. It will explode only as it reaches its maximum pressure limit, right? So here again, P1 V1 by N1 T1 equals to P2 V2 by N2 T2. You're given about one case, you're asked about the other case. Okay, pressures, you're given this is P1, this is P2 we have, this is T1, that is T2. So volume remaining the same because the volume is definitely the same cylinder we are talking about. So volume is same and number of moles also same. They are not going to change. So P1 by T1 equals to P2 by T2. P1 is 15 atmospheres by T1 we do not know, let that be T, is equal to P2 is 2 atmospheres by T2. Don't consider this as 27 degrees, go for 27 plus 273, which is your 300 Kelvin. So which is 300. So which means T is 2250. That would be your temperature in Kelvin scale. Your answer here is in Celsius scale. What you would do, 2250 minus 273. That would be your degree Celsius. I'm not calculating that. You would do it. Okay, so one case is given to you, the other case has been asked to you. You would just blindly go with P1 V1 by N1 T1 equals to P2 V2 by N2 T2. Next, moving on with question number 10. A balloon having 8 grams neon, 8 grams neon, and radius is 20 centimeters is pricked, and 7 grams of neon has effused. This is in a balloon, it is being pricked, and then 7 grams of neon is being effused from it. What will be the radius of the balloon under similar condition? Here, radius is how much? In the second case. So same again, if I consider P1 V1 by N1 T1 is equal to P2 V2 by N2 T2, pressure is constant, the same thing. Okay, so N1 by V1 or V1 by N1 is equal to V2 by N2 because see, because some amount of gas is being exploding out. So number of things will be changing there, number of molecules will be changing. So V1 by N1 is equal to V2 by N2. So V is what? Volume here, radius, in terms of radius is being given to me. So volume is 4 by 3 pi r cube. So 4 by 3 pi r1 cube by N1 is equal to 4 by 3 pi r2 cube by N2. So 4 by 3 pi and 4 by 3 pi I am going to cut. So R1 cube is 20 ka cube by N1. N1 is nothing but number of moles. Number of moles is given mass by molar mass. Given mass is 8 by molar mass of neon. I am writing it as Mr, or you write it as your neon has got 20 molar mass. You can write it by 20 because that is going to be anyway cut out. So I'm not writing it. That's it. R2 I do not know. R2 square by N2. N2 is my how much now? This is my how much is the molar mass? That is what we are asked about. Your 1 gram is only left out. 1 by, because 7 grams have been effused out. So now what will be the radius of the balloon? 7 grams went out. So only 1 gram left out in the balloon now. So that radius of the balloon is being asked to us. So this goes off. Now this is 20 cube by 8, which is 20 by 8, the whole cube is equal to R2 cube. 20 by 8, which is 10 by 8 is your answer here. Okay, so that would be your radius of your balloon there under these conditions. Now, one second. This is 20 by 2 the whole cube. No, I'm so sorry. 20 by 2 the whole, because 8 is 2 cube, right? So 20 by 2 the whole cube, which is 10 cube is equal to R cube. 10 is equal to R2. That is what we got. Radius is 10 now. Initially, it was 20 centimeters when 8 gram was there. Now it is 10 centimeters when 7 grams is there. So that is how we go with. Next, moving on with your next question. Question number 11 here. Coming up your way. Yes. A student put a reaction mixture in a round bottom flask at 27 degrees Celsius on flame. After some time, the temperature of the flask was 477 degrees Celsius. what fraction of air would have been expelled out? It means he is doing it in an open flask. Open flask, same pressure, same pressure. Okay. So P1 V1 by N1 T1 equals to P2 V2 by N2 T2. Here, if I say pressure same, and I would say volume also is same. Why? Because it is the same box we are using for my reaction. Whatever the box is there, the volume occupied by the gas is nothing but the volume occupied by the container here. So V is also same. So N1 T1 is equal to N2 T2. All right. So thereby we can go with initially how much was that? What fraction of the air would have been expelled out? So now you can calculate that. So here my N1, I don't know. T1 is take it as 300 Kelvin, and this will be 477 plus 273 Kelvin, right? So this is your 750. So N1 into 300 is equal to N2 into 750. So N1 by N2 is equal to 750 by 300. Now you would do this and you would get the answer there. All right. So then next 12th one. Temperature and pressure in Delhi is 47 degrees Celsius and 800 millimeter of mercury. Wherein in Mumbai, this is for Delhi, and for Mumbai, Mary Jaan, yes. And in Mumbai, it is 27 degrees Celsius and 750 mm of mercury. What is the ratios of their densities? Now, density ratio is what? D1 by D2, right? Is equal to under root, you would just do the same thing, yeah? Go on with the same, your reactions, gamma 1 by gamma 2 is equal to, right? Gamma 1 by gamma 2 is V1 by T1 by V2 by T2. All those, equations at one state you write once and then you. Yes, Bacha. So we have known also density is equal to what? Pm by RT, because we have derived that formula as well. PV is equal to nRT. P is equal to number of moles ke jagah. Number of moles is given mass by molar mass. This is my given mass by molar mass. This V is coming here, RT. And what is M by V? M by V is my density. So density D is equal to PMR by RT, PM by RT. So I would say D1 is equal to PM1 by RT1, D2 is equal to PM2 by RT2. Now divide. So density 1 by density 2, this is what it is being asked to you. Pressure being the same, not pressure being the same, I mean molar mass of this and that being the same, I would say same densities of the air it is being saying. So molar mass we do not know, we just consider it to be the same thing there. And now the density ratio is what? This cancels off, and yes, temperature matters, R will not matter. What is P1? P1 is 800 mm by T1 is 47 plus 273. Don't forget to change this. If you don't change this, you are lost. Okay, so this is 320 by 320 divided by D2. What is my D2? D2 is P, pressure, which is my 750 by T2, which is 27 degrees, can be written as 300 Kelvin. So this is 800 into 300 by 750 times 320. Now you go on cancelling this. I have done it with my calculator. You use your brains. You do it very quickly. This answer is going to be 1 here. All right. So now moving on with the next one. Or why to use calculator? Yeah. Come on. Okay. This is 0 gets cancelled. 0 gets cancelled. 8 table or 16 table, 16 twos are 16 fives are, right? So now this also 5 and 12 fives are 75. Now here again, you just cancel off these things, right? So 24 and this would be, oh, it is not getting cancelled this way. There is some 800 times 300 by 750 times 320. Check out one more time, bacha. I hope my calculation is right. Yeah, 800 times 300 by 320 times 750. Yeah, done. This is done. Now, yeah, 15 5s are 75, 15 2s are, and this turns out to be 16s are, yeah, 16 5s are 80, 80, that is one. Yes, one only. All right. Next, moving on, question number 13. 13 also is literally the same. 13 also will be the same. I hope my voice is a little cracky, but please do bear with my voice today. Yes, density of a gas is 16 at normal temperature and pressure. Density is 16 at NTP. At what temperature? At NTP. At what temperature the density is 14 if pressure remains constant. So I know density 1 by density 2 is Pm by RT by Pm by RT. Here M cancels off. R cancels off. This is T1, this is T2, P1, P2 I am taking. And pressure also cancels off because it is being said that pressure remains constant here, right? So density 1 by density 2. Density 1 is 16 by density 2 is 14 is equal to T2 by T1. So this is 8 by 7 is equal to T2. I do not know which is T by T1 is your normal temperature and pressure, which you take it as 273 Kelvin. So here you get T is equal to 8 into 273 by 7. Yeah. So this calculation, you would get your answer there. Next, moving up with 14, a closed flask contains water in all the three states at 0 degrees. Okay, this is a closed flask, has got water in all the three states at 0 degrees, all its three states at 0 degrees. In this situation, average kinetic energy of water molecule will be greatest in which state? Average kinetic energy is always dependent on the temperature and the random motion of it, the velocities of it, right? So velocity for a gas, it is more, so definitely it will be greatest in the vapor state. You're given all the options here, same in all the three states, greatest in the liquid, greatest in the solid, greatest in the vapor. Greatest in the vapor is more because we are asked about the kinetic energies. Next, two flasks A and B have capacities. This is flask A and flask B has got capacity 1 liter and 2 liter. Each of them contains 1 mole of a gas here, 1 mole of a gas there. Temperatures of the flask are adjusted that average speeds of molecule in A is twice as those in B. So what do we mean by that? Average of A is twice average of B. So do you all remember that average का formula? Okay, U average क्या है? U RMS क्या है? U most probable क्या है? Most probable is 2 RT by M. And RMS is 3 RT by M under root. And average is 8 RT by pi M. This is my average. All these three should be in your fingertips. Now, average of A, which means under root 8RT, or I would say TA by pi M, molar mass of A, is equal to 2 times under root 8RTB by pi and molar mass of B, right? And it says that each of them contains 1 mole of the gas, it would be the same gas they say. So therefore molar mass is also gone, pi also gone. Then R also gone, 8 also gone. So squaring on both sides, TA is equal to 4 times TB. That is what we have got. And what is that they asked us? The pressure in the flask would be. Now, what do you mean by pressure? Pressure is dependent on what? TA by TB into VB by VA, right? See, PV is equal to nRT, nothing but PV is equal to nRT PA VA. And then PB VB is equal to nRTB, right? So now since it is the same, this is 1 liter and 2 liters. I'm just substituting it. PA by PB, and volume of A is 1 liter, volume of B is 2 liter, NR gets cancelled. It is TA by TB. TA is 4 times TB by TB. Now TB gets cancelled. This 2 goes to the other side. PA is equal to 4 times PB, or then the pressure in the flask A would be 4 times PB, or if they ask you pressure in the B would be 1/4 of A. So that is how you can go with. So move on with the next question here. Coming up next, 16th one. This is question number 16 going on. Yeah. Velocity of C in the above figure. See, there is something given like this. This is fraction of molecules. Fraction of molecules. Like this, it goes and comes like this here. And this is in the fraction of molecules is given in this relation. And this would be my most probable speed. Definitely, this is always my most probable speed, UMP, always. And most probable speed is nothing but under root 2RT by M. That is my UMP. MP under 2 letters, you remember that way. Most probable speed 2RT by M. RMS under 3 letters, 3RT by M. Average is an average 8RT by pi M, you remember. Next, 17th question. A closed vessel contains equal volume of N2 and O2. This is equal volumes of N2 and O2 at a pressure of P, at a pressure of P. If N2 is removed from the system, if N2 is removed from the system, then the pressure will become how much? Now the pressure will become half only, because equal volumes are there, right? Equal volumes occupy equal moles, right? So half of the moles are being removed. So pressure also reduces to half, right? So next, according to the kinetic theory of gases, which option is true? Pressure exerted by given mass of a gas is proportional to the mean square velocity of the molecules at constant volume, which is true. Yes, it is according to the kinetic gas equations and ideal gas laws. Then option B says pressure exerted by gas is proportional to the root mean square velocity. No, it is proportional to the mean square velocity, not root mean square velocity of the molecules at constant volume. And yeah, root mean square velocity is proportional to the temperature, they say. Is inversely proportional to the temperature, they say. No, it is proportional to the temperature. And kinetic energy of molecule is directly proportional to the temperature in degrees centigrade, they say. No, it is not degree centigrade, it is degree Celsius, it is degree Kelvin, it is Kelvin. Kinetic energy is directly proportional to its Kelvin temperature. So option A is correct, which says according to kinetic theory of gases, pressure exerted by given mass is proportional to the mean square velocity of the molecules at the constant volume. Okay, then which of the following is incorrect statement? Van der Waal constant is a measure of attractive force. Yes, it is true. Question number 19 has got some good valuable information. What is Van der Waal constant? A is a measure of attractive force. A is a measure of attractive force, and B is also called as co-volume or excluded volume. This is excluded volume per mole, and for n moles it will be NB, which is also right. And B is expressed in liters per mole. Yes, these many liters per mole is excluded volume, which is also true. And it says B is 1/4 of the critical volume. No, wrong. VC is 3 times B. So B is 1/3 of the critical volume is correct, not 1/4. So right at the beginning, I have given you some few formulations for constant pressure, your critical pressure, critical temperature, and critical volume. Please go through that equations one more time. You will get that piece. VC has to be 3 times B. It says 4 times. It is wrong, right? Next, van der Waals constant A and B are related with attractive forces and volume of the gases. A and B are attractive forces and excluded volume, more appropriately, go with excluded volume. Then a gas derived from ideal behavior at high pressure because its molecules have got what? High pressure, may you have more of repulsive forces dominate. Gases deviate from ideal behavior at high pressure because they have more amount of repulsions also. Okay, they have repulsive forces. Try, understanding that as you bring them close, they do want to move apart also due to the collisions and all. Next, when do you expect a real gas to behave in ideal gas? We have just now seen your Z value, your compressibility factor value there at high temperature and low pressure. This we have discussed in class also. HTLP, HTML I have asked, if you remember, right? What is HTML? I have asked you as a doubt of HTML. So HTLP, remember, high temperatures and low pressures, ideal gases, your real gases do behave as the ideal gases. Okay, number 23 then, dominance of strong repulsive forces among the molecules. If you have repulsive forces, molecules tend to move apart from each other, thereby volume of the real gas is more than volume of the ideal gas, which means Z value is greater than 1. We have just now discussed V real by V ideal is the Z value, hence it is greater than 1. Next, moving on with the next question. Next question again is a numerical one. So please do take care of your theory part as well, because this chapter has got good amount of theory. Just by looking at the question, you can answer it. Next. Moving on with 24, 1 mole of SO2, okay, 1 mole of sulfur dioxide occupies a volume of 900 ml at 24 atmospheric pressure at 27 degrees Celsius. Then the gas is showing negative deviation, gas shows positive deviation, gas shows no deviation, cannot be determined. These are the things which has been asked, which means I want Z value. Z is what? Z is your V by your V real by V ideal. So let us first bring out what is my Z value for this. V ideal. What is V ideal? Is PV is equal to nRT, V is equal to nRT by P, right? And R is 0.0821 into T is 300 by P. Pressure is 24 atm, which is roughly closely somewhere around 1.023, right? And here we are talking about this pressure at which thing? Yeah, Z is equal to your V real by V ideal. V real is given to you as 0.9. 900 ml is given to us. I'm taking it in liters. 0.9 is 900 ml is 0.9 by volume here is 1.023, which is less than 1. Definitely, I don't need to calculate it. Less than 1. Less than 1 ante negative deviation. Negative deviation matlab they are showing attractive forces. Attractive forces are being shown here, right? Next, 25, at critical temperatures and low pressures, it says critical temperatures, and critical temperature is always less than the Boyle's temperature. Okay, at critical temperature, which kind of forces are dominating at critical temperature? The temperature is less than the Boyle's temperature, therefore attractive forces are dominating, and attractive forces, which means molecules are coming closer, which means it is occupying lesser volume. Therefore, V real by V ideal, it shows the negative deviation. So Z is less than 1 here. Next, 26, theory part, this is again, huh? Next, 26, gas is easily liquefied at high pressures and low temperatures. High pressures, low temperature, easily liquefied, because as you have to liquefy the gases, the molecules should come close to each other. Now, if they have to come close to each other, you have to apply more pressure, right? So high pressure, low temperature. That is how your soda maker and all, as you see, bahar जो सोडा के ठेले पे जो सोडा जो बनता है, that is at high pressures and chilled bottles, chilled low temperatures. Next, which of the following is incorrect statement? They say, see, try to analyze these statements clearly. Please listen to me very carefully. Ideal gases are having Z is equal to 1, cannot be liquefied. Is that the incorrect? Z is equal to 1. Ideal gases cannot be liquefied. True statements. When Z is greater than 1, gases are easier to compress. Yes, because volume is more. As the volume is more, you can compress them. Then when Z is less than 1, easier to compress. Then when Z is greater than 1, real gases are difficult to compress. Yes, real gases are difficult to compress when Z value is greater than 1, which says repulsive forces dominate. Yes, that is my incorrect statement there. So option B is my incorrect one there. Next, question number 28, I am going on with. At the critical temperature, as there is no difference between the gaseous state and the liquid state, the critical temperature, that temperature wherein there is no difference between your gaseous state and your liquid state, just it is being liquefied. That temperature at which the gaseous state is being converted to liquid, that is your critical temperature. The meniscus between liquid and vapor state disappears. The upper meniscus, lower meniscus, we say, that disappears. The liquid ki paina, kinda, you will not have anything. It will be straight. It will be just straight. Okay, the meniscus between liquid and the vapor disappears, as there is no difference between your gaseous state and the liquid state at critical temperature annadu kabatti, because it said that it is critical temperature. I am talking about this. Next, 29. If for a critical parameters, you are given PC is given to you as 2 atm, TC is 47 degrees Celsius, approximate value of VC is how much? So we have just now written some formula as well. TC is equal to 8A by 27 RB, we know. And PC is equal to A by 27 B square, we know. And I'm just trying to divide these two. 27 gets cut, A and A gets cut. So TC by PC. TC is 47 degrees Celsius. Nana, 47, please convert that. 47 degrees Celsius, 47 plus 273, right? So this is 15 here, this is 350. All right, so 47 degrees Celsius, which is your 350 Kelvin, by PC, which is 2 atmospheres, is equal to, B gets cancelled here, B by R. So from here, you can bring out your value of this. And then VC is equal to 3 times B. VC is equal to 3B, which means 3 times B value is R into 350 by 2. Just calculate this. You will get the value. R, take it as 1 by 12 for easy convenient values. This is 1 by 12 I'm taking for convenience. So this is 400. This is 3 into 25, I would say. And 75 by 2, somewhere close to, you can just go with your values there. Okay, then next question coming up. Then question number 30 here. Just be careful with your calculations, Nano, that's it. And your theory part, very important, understanding the concept there. Next. Question number 30. At low pressure, van der Waals equation for 4 moles 4 moles of a real gas will have its simplified form as what? At low pressures, they say. At low pressures. Then at low pressure, my B part can be neglected because at low pressures, my B is neglected because the volume occupied is negligible only, right? So negligible volume, I don't have prominent B, getting occupied there. Low pressures, my gas particles are moving apart from each other. They are not occupying much of volume there. So they're not coming close to each other, not occupying much volume. Here, B is equal to 0, I would consider. So then my P plus this will be my 4 square into A by V square, A n square by V square, na? P plus P my A n square by V square is equal to times V is equal to nRT, which is 4RT. Now from here, if I have to bring out my equation, I'm just bringing the 4 onto that side and then take out PV square plus 4 square into A by V square is equal to 4RT. Now again, this also comes to the left side. Divide by RT, nothing but divide by RT on both the sides. You will get your equation there. All right. Or you want me to do that? I can do that. Yes. So that would be my here. Let's go on with this. So this is V square here. Yeah. Times V also we have here. This cuts off. Now this is PV plus 16A by V is equal to 4RT. 16A by V is 4RT. Now PV is equal to 4RT minus 16A by V, 4 common, RT minus 4A by V. So there V, let that be V there, P को right side भेज दो, you will get your answer. That's it. Option 2 is your answer there. All right. I'm moving with the next question, 31. According to the kinetic theory of gases in ideal gas, between two successive collisions, always gas molecules travel in straight path. Bache, remember that, not in random portion. Yes, gases do travel in random, directions, but they asked you between two successive collisions. That's the most important trick you have to find there. Between two successive collisions, that is most important. Okay, next 32, question number 30. Yeah, moving on with question number 32 here. Again, this is a stoichiometric question also based on. Yeah, this is a nice question to go with. 32. What volume of hydrogen gas at 273 Kelvin and 1 hydrogen gas ka volume is how much at 2? Write down the information, Anna. Whenever you're given something, please write down information like this. What volume of hydrogen gas at 273 Kelvin and 1 atmospheric pressure will be consumed in obtaining 21.6 grams to obtain 21.6 grams of elemental boron, which has got the atomic mass as 10.8 given to us. That only we should take from the reduction of boron trichloride by hydrogen. So I have to use my equation, boron trichloride. Okay, so BCl3 plus hydrogen will give me boron plus definitely HCl only I get. So now I first balance this also. Boron, chlorine. Yes, I have to put my 3, but 3 will not suffice my for that. So this is my 3H2. Yeah, this will be my Cl has got 6 of them, 2 of them. Now here is 2. Done. Now this is 2x, this is 3x, this is 2x, this is 6x. This is my equations. So now accordingly, I would just write down the information also. 21.6 grams of boron is what I got. I write my moles first here. Moles is given mass by molar mass So this is 2. So here my 2x is equal to 2 moles, which means x is equal to 1 mole. And here 3x moles is required. 3x matlab 3 moles is required for this. And 1 mole is always 22.4 liters. So 3 moles will be 3 into 22.4 liters. That will be somewhere around 67.2 liters is your volume occupied. This is definitely your stoichiometric question. All right. Then 33. As the temperature is raised from 20 degrees Celsius to 40 degrees Celsius, average kinetic energy of neon atoms changes by what factor? Average kinetic energy, that depends on temperature. Yes, kinetic energy is equal to 3 by 2 RT1. Ke1 is equal to 3 by 2 RT1. Ke2 is equal to 3 by 2 RT2. I say divide. Okay, always this ratio. Ke1 by Ke2. Ke1 by Ke2 is equal to T1 by T2. And T1 is 20 degrees. Please change that. It is 20 plus 273, which will be my 293 Kelvin. Okay, 293 Kelvin by your 313 Kelvin. So Ke1 is equal to 293 by 313 times Ke2. That's it. Okay, by a fraction of how much times? That is what we have written there. Next, 34, last couple of questions. Which one of the following statements is not true? They say not true about the effect of increase in the temperature. Remember, these theoretical questions, damn important. You can just see the question and within seconds you can answer it. 4 marks in your pocket. So yes, which of this is not true? Now the options are: area under the distribution curve remains the same as under the low temperatures. Yes, because area under the Maxwell's distribution curve always remains the same, because this curves goes on flattening itself, because you should go with the area same, because area under the curve always will give me those number of molecules, and that is not going to change there. So therefore area flattens. Yes, area under the curves distribution curve remains the same. Yes, it is true. And the distribution becomes broader. Yes, as you can see, first case, second case, and the third case, it is becoming broader as your most probable speed is getting increased. Number of particles that attain that higher speeds will decrease. So therefore, particles are getting decreased. Number of particles is decreasing there, but the other particles are the same only, right? So therefore, number of particles should remain the same, the area should remain the same. Therefore, your curve gets broader and broader. Most probable speed increases. Yes, initially this was the most probable speed. And now for the yellow one, this is the most probable speed, UMP1, UMP2, and here is my UMP3. As compared to broader curves, UMP, most probable speed is increasing definitely, but the number of particles that has this speed is less. Okay, so remember that those fraction of particles are getting decreased definitely, but those most probable speed is definitely increasing there. Next, it says fraction of molecules with the most probable speed increases. No, it is wrong. Option C is wrong, definitely. It decreases. Fraction of particle is decreasing. This curve is very, 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 very important curve. Okay, so in case you have any doubts, please do ask me in tomorrow's class only. Okay, because I want you to finish this today. All right, tomorrow's class, you will ask me any of these doubts. Next, equal masses of methane and oxygen are mixed in empty container. Methane and oxygen equal mass, here M, mixed in container at 25 degrees Celsius. The fraction of the total pressure exerted by the oxygen is, fraction of the pressure exerted by oxygen is nothing but number of moles of the oxygen there. So number of moles of oxygen is X by 32. I don't know that, right? And xi of oxygen, let us bring out xi of oxygen is number of moles of oxygen by number of moles of oxygen plus number of moles of CH4. This is X by CH4 or M by CH4, I would say, mass, given mass by molar mass. And for this, number of moles of CH4 is given mass by molar mass here is 16. So now for xi of oxygen is nothing but mole fraction of oxygen. It is m by 32 by m by 32 plus m by 16 into 2 into 2. This is m by 32 by 3 by 32. 3m by 32. So m gets cancelled, 32 gets cancelled, 1 by 3 of the total pressure. Xi of O2 is 1 by 3. So 1 by 3 of the total pressure is what answer is. Next, coming up with 36, the question there, 10 power. One second, I will scroll on. Yeah. Last two more questions, bache. 10 power minus 4 decimeter cube. 10 power minus 4 decimeter cube is nothing but the liters. 10 power minus 4 liters water is introduced into a 1 liter flask at 300 Kelvin. How many moles of water are there in the vapor phase when the equilibrium state is established? Vapor pressure of water at 300 is, at 300 pressure is given to you as 3170 pascals, and R value you should take it as 8.314. Just substitute the values. Nana, number of moles is 3170 into 10 power minus 3. That is what is your kilopascals given to you. Change it by 8.314 into PV is equal to nRT. Just apply PV is equal to nRT. You will get the value. Next, the last question for the day, 37. Longest mean free path. So longest mean free path is nothing but your lambda value, which is 1 by root 2 pi a square n. Okay, this will be your formula for the longest mean free path. Free path, how much is the path given there? How much you can go with? That is the question there. So for which A stands for your, the distance there, attractive forces there. And when you have smallest diameter, you will have the longest free path. So smallest diameter for options A, B, C, D, you're having hydrogen, nitrogen, oxygen, Cl2, obviously smallest diameter for your hydrogen, and that gives you the answer because that is 1 by A square given to you. So inversely proportional. So as it is inversely proportional, smallest will have your longest mean path. So hydrogen would be your answer there. So that's it for your gaseous state. So most of the questions, all of the types of questions we have discussed in the previous class and even in this class. So especially for the second years, I want you to go with these recordings meticulously with utmost diligence is required here. So any of the doubts, you will come back to me the next day only. All right. So that's it for today then. Happy learning, bachcho.